Okay, guys, standard 10 exponential growth. This is going to be set up a little bit differently than what you are used to, but I think it's going to be really good and help you guys really understand exponential growth. What an exponential function is it's a function in this form. You're going to want to write this down for sure. And it creates a pattern. It creates a list of numbers where the pattern increases or decreases with multiplication. So you guys might be used to like a list like this: 1, 4, 7, 10, and you add 3 every single time. That's something that we've worked on a lot last term. But what we're going to be dealing with now is something like this, where you don't add the same amount every time. Now we multiply by 2 every time. So we're talking about multiplying by, the pattern is multiplying. And what we're going to be talking about right now is exponential growth. So that's where it increases. So increasing pattern. And some of you guys may have heard people be like, oh my gosh, it's increasing exponentially. That means that it increases really fast. Whereas if it increased linearly, it would just do the same thing each time. But exponentially means that it increases really quickly. Corbin, can you please stop that? Because I'm doing a video. Thank you. All right. Here's an example of a situation where something increases exponentially. There are 32 bacteria on a doorknob at the beginning of a day. The amount of bacteria increased by 30% every hour. That's disgusting. So we're going to talk about 3 things here. We've got a growth rate, a growth factor, and an equation. And we're going to be dealing with this a lot this whole time. A growth rate is telling you how much it's growing by. So the amount of bacteria on a doorknob at the beginning of a day is 32. So 100% of its population is 32. It keeps that 100% and then adds 30% more. Growth rates are percents. So this would be every hour, your rate is 130%. So one thing you guys need to remember for growth rates is that we're always talking percent. And with growth rate, you do 100% plus whatever percent it increases by. Okay. Now we do, now a growth factor is pretty easy once you have your growth rate. You take your percent and you turn the percent into a decimal. So how you turn percents into decimals, so we have 130%. What you do is you move the decimal back 2 spots. Always, you move it to the left 2 spots. So your growth factor is 1.30, or most math people would just write this as 1.3. But this means that there's been an increase of 30% of the bacteria on the doorknob. Now your equation, and I showed you guys the equation up above. It's this weird thing right here, and it's really not that bad. So we're going to copy down that equation here to the power, so a times b to the power of x, and we're going to define some things. This here is the starting point. So we know how many bacteria were there at the beginning. 32. So A is going to be 32. B is your growth factor, not the growth rate. It's the decimal. So here it's going to be 1.3. So our equation, y equals, we started with 32 bacteria and it increased by 30% each hour. Now I'm going to show you guys real fast what this looks like on a graph. So I'm going to go to Desmos here. And we said 32 to the power of x. Okay, so I'm going to zoom out. And look what happens, you guys. So it starts at 32. And is it increased? So at 0 in the morning, it was 32 bacteria. And look what happens. Look how much. Holy cow. It increases so fast. This is crazy exponential growth. I really hope somebody goes ahead and wipes that doorknob because that's disgusting. If nobody cleans the doorknob, how many bacteria will there be in 5 hours? So another thing I want to tell you guys about this equation is X is the time, usually, and Y is the total number. And so in this case, we want to know the total number after 5 hours. 5 hours. So I'm going to go back to Desmos, and what I'm going to type in, I'm going to get rid of this, and I'm going to type in 32 parentheses 1.3, and then I'm going to do the caret, and the caret is Shift 6 on your on your keyboard, and then I'm going to put in, we wanted to know 5 hours. After 5 hours, you guys, there will be 119, let's say. Let's round that up. There'll be 119 bacteria after 5 hours. 119 bacteria. Get out the Lysol wipes or whatever we call them. I get the Up and Up brand. I'm not selling anything. Oh, bacteria. It's not spelled right. Okay. So let's talk about selling stamps. When Sam was in 7th grade, his aunt gave him a stamp worth $2,500. So a stamp, like a stamp that you would use to mail a letter, sometimes they're worth a lot if they're like really vintage. Sam considered selling the stamp, but his aunt told him that if he saved it, it would increase in value. Okay, so we know the starting point for the value of this stamp was $2,500. And that it's increasing. Increase means growth. So Sam saved the stamp and its value increased by 6% each year. All right, so we're going to find the growth rate and the growth factor. So when it says increased by, that means, remember, for the growth rate, this is a percent. The rate is a percent. We do 100% plus 6%. And so that would be 106%. The growth factor is where you take that percent that we got right here and you put it into a decimal. So I have this, and I'm going to move the decimal back 2 spots. 1.06 is your growth factor. Write an equation for the value of Sam's stamp after n years. Well, its initial value was $2,500. It increased by 6% every year to the power of x. Make sense? Okay, now we're going to use that equation a little bit. If he saves the stamp for 7 years, how much can he expect to sell it for? Well, so it started out with this. 1.06. It was only 6%, not 60%. We're wondering about 7 years. So I'm going to go ahead and type that in to Desmos. 2,500, 1.06 carat 7. Whoa, $3,759. Okay, $3,759. If he can hang on to that thing, he'll make that much money off of it. Wow. Suppose the value of this stamp increased by 20% each year instead of 6%. The first question is, what is the growth factor? Now remember, the growth factor is a decimal. We need to find the growth rate first. So the growth rate is 100%, always 100% plus 20%. That is 120%. Now we can find the growth factor. 1.20 or 1.2. This here is the growth factor. Write an equation that represents the value of the stamp for any year. Well, we have a new growth factor, so what we're going to change is the growth factor. It still was initially worth this much. Now, that's our new growth factor. Okay, what do you guys think is going to happen here? How much is Sam going to expect it to be worth after 7 years? Do you think it's going to be more or less than $3,759? Let's see. So I'm going to go back here and I'm going to do 20% instead. Holy cow. $8,958. $8,958. That goes right here. After 7 years. Oops. If I could write, that'd be amazing. Oops, that's a 7. All right. Now, Sam was like, Auntie, I think that you're a little cray. This sounds ridiculous. A stamp, a tiny piece of paper, is worth $2,500. Don't think so. So he brought it in to be appraised. After the expert looked at it, they said that the value of the stamp can be modeled by this equation. What is the growth factor? Remember, this is a decimal. What is the growth factor in this equation? 1.15. What is the growth rate? 115%. So it increased by 15% each time, right? It maintained 100% of its value and then increased by 15 more. What's the initial value of this stamp? Well, the appraiser, the expert, said only $1,200. Using this equation, how much can he expect it to be worth after 7 years? Well, 1.15 to the power of 7. He's very obsessed with this 7-year thing. Is that when he goes to college or something? Corbin, stop with the no button, please. 3,192. Okay. $3,192. Suppose the expert gave him this equation instead. Ooh, this is interesting, you guys. How much could Sam expect the stamp to be worth after 7 years? If this is what he said, the expert said, or woman, I don't know. Okay, so I need to change 3,000, 0.9, and 7. Ooh, $1,435. Oh, you guys, was that an increase or let's say that, so if the expert gave him this equation, this means he said it's valued at $3,000 today. But what happens after 7 years? Is this still an example of exponential growth? I don't think so. This is no longer exponential growth. And I wonder if it has to do with this number here being less than 1. Because it wouldn't be 100% plus something. It would be 100% minus something. Interesting. This is no longer growth, not growth. You want to know what it's called? You'll have to wait for standard 11 for that. Let's see what's next. Oh, that's learning target number 2. So now using this information, you guys, go ahead and take the quiz on this standard or learning target. What else?